In this next subsection, I want to discuss the simple solutions to the range min query problem. The sparse arrays will be the final result. For today, we'll leave it just with the most primitive ideas for implementing range min queries. There's two obvious solutions at the extreme ends of a scale, where the scale is from doing nothing at pre-processing time to doing everything at pre-processing time. So one is doing nothing, no pre-processing at all. And whenever someone asks for a minimum in a range, you just find that minimum by walking through the entire range and keeping track of the minimum. That is trivial to do. I'm just listing it here to translate it into our notation. So that is a constant time pre-processing, actually 0, but okay. No pre-processing, constant time pre-processing, linear time query, because the range can be as long as the entire array. That's not very interesting, and it won't get us closer to our final goal. The other extreme end is, well, there's only so many possibilities to ask for ranges. Namely, I and j, I can start at 0, and they have to be sorted. Well, no, it's less than n because we start counting at 0. So there's only n squared solutions for this, n squared choices for I and j. So we can create one big two-dimensional array for I and j, and just store the solution for RMQ there. So the query is one array lookup, well, maybe in a two-dimensional array, but you can even map this to a 1D array if you wanted. So we can compute every individual answer in linear time. There's n squared answers. That gives us a cubic pre-processing time, but constant query. It's probably not good enough to be interesting, but at least it shows what is possible at the extreme ends. A simple observation is that we can get the pre-processing time to quadratic, so filling the array in constant time. And you can do this because if you have your current range I to j, you can take one element off, the last say. And then what is the possibility for the range min query in I to j? You can find where the range min is if you leave out the j, and that's maybe here. So then RMQ ij is either RMQ I up to j minus 1. This you cannot see. It's either RMQ or the result is j. And these are two different options, so you can take constant time to compare the values at that position, and then insert into your array m, whichever was the smaller one. So by filling the array in a somewhat smart order, going from those with a small range to those with a bigger range, is enough to get this result: quadratic pre-processing time, constant query time. That's what you can easily do. Unfortunately, this is still far away from our ultimate goal of a linear pre-processing time, and we will continue tomorrow with our quest towards this goal.